again welcoming you all to third lecture of week 11. So, we continue our discussion on analog to digital converter. In this lecture, we discuss about design of some different kinds of analog to digital converter. We started with flash type AD converter in last lecture, which was very fast but requires a lot of hardware. Then we looked at some counter type AD converter. One was up counter based AD converter and other was up down counter based AD converter. But in both the converters, conversion time required was t clock into 2 to the power n minus 1, which is very high. Today we shall be discussing some more design of AD converter. Let us start with AD converter design of successive approximation type. This is also a counter based AD converter. This AD converter works on same principle as principle of binary search done in software. Now, what binary search method does? If we have a sorted list of numbers and if we want to search for a number, then this method starts with the middle and takes a decision. Either it has to look at left side or right side of all numbers. Then again it starts with middle of that half and takes decision again. This process continues until we get the number we are looking for. So, before understanding operation of this converter, look at the schematic diagram to understand the design. Design of successive approximation type AD converter requires one comparator, one n bit DA converter and one successive approximation register, which is also set as SAR. Here also there are two control signal given to SAR register, SOC, that is start of conversion signal, and EOC, that is end of conversion signal. SOC is an input signal and EOC is a output signal. When we want to start the conversion, SOC is set 1 and when the conversion is complete, EOC is set 1. So, let us understand how this design works with the help of an example. Suppose we are using a 3-bit successive approximation register. It means we have range from 000 to 111, that is from 0 to 7. At the beginning, output of successive approximation register is set 000 and as soon as process starts, most significant bit of SAR output is set to 1. It means SAR output is 100, which is fed to DA converter, and DA converter gives equivalent analog output, which is named as D here. Here decimal equivalent of 100 is 4. So, in the range of 0 to 7, 4 is almost at the middle point. So, we have searched the middle point in this way. Now, comparator will check whether our analog input A is less than or greater than D. If A is less than D, then we have to go down. So, we change the MSB value from 1 to 0 and set the next bit to 1, and if A is greater than D, then we leave MSB as 1 and set the next bit to 1. Now, SAR output will become 110. 110 means 6, which is midpoint of upper half part. Again, comparator will compare this output with the analog input, and based on the output 1 or 0, it will take the decision. This process continues until we reach the LSB, and at the end output of SAR is equal to our digital output. So, if this is an n bit converter, number of steps required will be n. We will understand this with the help of example. So, instead of 2 to the power n minus 1, we need only n steps here, which means this type of ADC is much faster. Let us understand this process with an example of a 3-bit ADC. On the left side, there is a curve where x axis is showing number of iterations and y axis is showing output voltage of DA converter. Also, on y axis dotted line is showing analog input voltage. So, at the starting SAR output is 0 0 0. As SOC signal become high, conversion begins and MSB is set to 1. So, DA converter output is 1 0 0 and corresponding level of voltage is 4 Vref by 8, which is approximately half of the full scale voltage. Now, when comparator compare it with input analog voltage A, comparator gives output high, because at this instant analog input is greater than 4 Vref by 8, as we can see in the diagram. So, the bit next to MSB is set high, that is SAR output become 1 1 0. Now, the level of DA converter output increases to a value 6 Vref by 8, which is approximately mid of upper half part of full scale voltage. When comparator compares 6 Vref by 8 with input analog voltage A, comparator gives output low, because at this instant analog input is less than 4 Vref by 8, as we can see in the diagram. So, the second bit is reset to 0 and next bit, that is LSB, is set to 1. So, SAR output becomes 1 0 1. Now, the level of DA converter output goes down to 5 Vref by 8. When comparator compares 5 Vref by 8 with input analog voltage A, comparator gives output 1, because at this instant analog input is more than 5 Vref by 8, as we can see in diagram. So, we get the final result as 1 0 1, and at this instant EOC is set high, because the conversion is complete now. In the right side there is a decision diagram which is showing all possible iterations. The blue path shows the iteration followed for our specific analog input. In the beginning MSB is set high, so we get output 1 0 0. DA converter output is now compared with analog input. Comparator output is 1, so we move to upper side of diagram and get the output 1 1 0. Now, again DA converter output is compared with analog input and we get output low. So, further we move to downside of diagram to get the output 1 0 1, and again DA converter output is compared with analog input and we get output high. So, our final result is 1 0 1. So, in this process we need only 3 iterations for conversion, as you can see in the decision diagram, and for n bit we need n iteration. So, this method is faster compared to counter type and tracking type converters. Now, let us understand the design of other kind of ADC named single slope ADC. A single slope ADC is not practically used, but when we understand the principle of operation of this kind of ADC, we will have a better understanding of the ADC which we are going to discuss after this. So, let us start single slope ADC. A single slope ADC consists of an op-amp based integrator, an electronically controlled switch, a voltage comparator, a binary counter, an AND gate and a control logic. In this kind of ADC, we use an op-amp based integrator and integrate reference voltage minus Vref, as we can see in the diagram. The output of the integrator is fed to comparator and is compared with analog input voltage A. This process of integration and comparison continues until integrator output is less than analog input voltage. The time t required by reference voltage to reach analog input voltage gives measure of input voltage. Let us understand this with the help of a mathematical expression. So, look at the mathematical expression. Output of integrator, that is V1, is given by minus 1 by RC integration of minus Vref. Here minus sign at the starting is because we have given input to negative terminal, and since Vref is also negative, slope of V1 will become positive. At time t, output of integrator V1 is equal to t. So, expression can be given as A is equals to t into Vref by Rc. Here in circuit, the value of R and C and also Vref remain constant. So, analog output is proportional to time t. So, we understood the principle of operation of single slope ADC. Now, let us understand the implementation of this principle with the help of a schematic diagram of single slope ADC. In the beginning, switch S is closed for small time and capacitor get completely discharged. So, output of comparator becomes 0. Also, counter is reset to 0 using control logic. Now, reference voltage is integrated and compared with analog input voltage. From diagram, you can see that output of comparator is fed to AND gate, and through this AND gate, clock pulses are applied to counter. So, when the output of comparator is high, clock pulse is applied to counter. As soon as counter get clock pulses, it start counting. So, whenever conversion process starts, the integrated output will be less compared to analog input. It means output of comparator is high, and due to that clock pulses can pass through AND gate and applied to counter, and counting starts. As soon as this integrated output voltage will become just equal to analog input voltage, the output of comparator will become low. Due to this, output of AND gate will also be low. So, no clock pulses will be applied to the counter. So, the final count of counter is directly proportional to analog input voltage. This way, a single slope ADC works. Now, here we know that the reference voltage value of R and C are fixed. So, slope of integrator will remain fixed, and we can see in plot on the right side that depending on input analog voltage, integration time varies. Means for higher input voltage, required integration time is also higher. Since here is only a single slope in each conversion, this type of design is known as single slope ADC. But the main problem with this kind of ADC is that if the value of R or C changes due to some reason like temperature or aging, then slope of ADC will also change. In such a situation, for same analog input voltage, we will get different integration time. Means for same analog input voltage, different binary output is obtained. This effect we can see in the plot on the right side. Due to this problem, accuracy of single slope ADC is very poor, and that is why this ADC is not used for measurement purposes. Now, in order to solve this accuracy related problem, we are going to discuss another kind of ADC named dual slope ADC. A dual slope ADC provide high resolution with good accuracy, but conversion time is slow. Due to this reason, this kind of ADC is not used where signal is changing very fast, like in data acquisition system where a lot of data is acquired continuously in order to process that data. This kind of ADC is preferred where signal changes very slowly. Due to its good accuracy and high resolution, it is used in measuring instruments where reliability is essential. In fact, they are commonly used in multimeters. Circuit component used in dual slope ADC are almost similar to single slope ADC. The only extra component used here is a two-way switch S2, which is used at integrator input terminal, and it switches between analog input voltage and reference voltage. And the purpose of switch S1 is same as it was in the single slope ADC. Let us see the principle on which ADC works. So, initially switch S2 is connected to analog input voltage. Once conversion starts, the integrator integrates analog input voltage A for a fixed duration of time, say T1. Look at the mathematical expression. Here output voltage V1 of integrator is expressed as minus 1 by RC times of integration of analog input voltage A. At instant t1, this voltage is equal to V dash. Suppose we can see this in the plot between V1 and t. So, mathematical expression at instant t1 will become V dash is equal to minus t1 by RC times of A. Now, after time t1, switch S2 is connected to reference voltage. Usually, polarity of reference voltage is negative and its value is more than analog input voltage. So, due to this negative reference voltage, integrator integrates in positive direction and the integration process continues until output voltage of integrator, that is V1, reaches 0. From plot, we can see that integrator takes t2 time to reach 0 output voltage. So, after time t1, this mathematical expression for integrator output can be given as minus 1 by RC times integration of minus Vref plus V dash, as we can see in expression. Now, at instant t1 plus t2, integrator output is 0. Putting the value of V dash in the above expression and after solving it, we get equation t2 is equals to t1 into A by Vref. This is our final expression. Here we know that t1 and Vref are constant, means time t2 is proportional to analog input voltage A. So, t2 gives direct measure of analog input voltage A. Here there is another plot which is showing that for different analog input during integration time t1, the integration slope is different, but during deintegration slope is constant for all the analog input because Vref, R and C are constant. So, for different input voltages, time required for deintegration is different, as we can see in the curve. So, as the value of input voltage increases, time t2 also increases. Now, let us have a look at schematic diagram of dual slope ADC and let us understand its working. Here, output of integrator is connected to one input terminal of comparator and other input terminal is connected to ground. So, initially when switch S2 is connected to analog input voltage A, the integrator integrates in negative direction, which means the inverting terminal of comparator is negative with respect to positive terminal, and due to that the output of comparator will be high. Now, this comparator output is connected to AND gate and clock pulse is provided to counter using AND gate. So, whenever the output of comparator is high, clock pulses are applied to n bit counter and counter start counting 0 onwards and it will count until overflow bit become 1. So, if we have a 4 bit counter, then counter will count from 0 0 0 0 to 1 1 1 1 and after that overflow bit will become 1 and counter value will become 0 0 0 0 again, and as soon as overflow bit become 1, S2 is connected to minus Vref. So, going from all zeros to all 1, the counter will take 2 to the power n minus 1 clock pulses, and at 2 to the power nth clock pulse the overflow bit will become high and switch is connected to minus Vref. So, we can say analog input A is integrated for 2 to the power n clock pulses. Now, since reference voltage is negative, integrators start integrating in positive direction, but from plot you can see that integrator output is still negative. That is why comparator output is high and clock pulses can pass through AND gate and the counter start counting from 0. This process continues until integrator output is less than 0. As soon as integrator output reaches 0, the comparator output become low and counter stop counting. At that instant, whatever will be the binary output of counter is directly proportional to T2, or we can say that this binary output is directly proportional to analog input voltage. Here total conversion time is equal to T1 plus T2, where T1 is equal to 2 to the power n times of clock pulses time period and T2 is equal to n times of clock pulse time period. So, if we see the worst case, when slope of both integration time and deintegration time are equal, in that case the magnitude of A is equal to Vref. So, the total conversion time is equal to 2 times of 2 to the power n times of clock pulse duration. Hence, we come to the conclusion that this type of ADC takes too much time for conversion, and conversion time depends on frequency of clock pulses and n, that is resolution. So, we have seen that T2 is independent of value of R and C. This means value of R and C will not affect conversion. That is why this kind of ADC gives good accuracy. So, today we discussed about 3 different types of ADC. If we look at the applications of ADC, ADCs are used in all the systems in which it is required to process, store or transmit analog input signals in the digital form. So, some of the examples are microphones, thermocouple, digital multimeter, and there are many more such examples. Now, let us look at a table which shows a comparison of different kind of ADC. Here we have compared a flash type, a counter type, a successive approximation type and a dual slope type ADC. If we look at the required number of clock pulses, in flash type we need only one clock pulse, and due to this the conversion time become T clock, where T clock is clock pulse time period. If we look at the counter type, it takes 2 to the power n minus 1 clock pulses. So, the conversion time becomes 2 to the power n minus 1 into T clock. In SAR type ADC, the number of clock pulses required are n. So, the total time taken by it for conversion is n times of T clock. And for a dual slope type ADC, number of clock pulses required are 2 to the power n plus 1. So, total time required by this kind of ADC is 2 to the power n plus 1 into T clock. If we look at the resolution of this kind of ADC, resolution of flash type ADC is low, counter type ADC is medium, SAR type ADC is also medium, but for a dual slope type ADC we get very good resolution, means high resolution. If we look at the cost, flash type ADC is very costly, its cost is high because we need too much components here. Counter type ADC and SAR type ADC, cost required for counter type ADC and SAR type ADC is low, and for dual slope ADC the cost required is medium. And if you look at the accuracy, flash type ADC is least accurate, counter and SAR type ADC are accurate, more accurate compared to flash type, but the dual slope type ADC is the most accurate among all. So, if we come at a conclusion, flash type ADC is fastest and dual slope type ADC is most accurate among all kind of ADC. So, let us look at some review questions. Here first question is, in successive approximation type ADC, the options are SAR register is a shift register, option B SAR register is simple binary up counter, option C is SAR register generates input to DAC by changing bits one by one from MSB, and option D is SAR register is binary down counter. So, here the correct option is option C, because SAR register changes the bits starting from MSB. Now, looking at second question, it is a numerical. A certain 8-bit successive approximation converter has 5 volt full scale voltage. The conversion time for input voltage 2 volt is 50 microsecond and the conversion time for input voltage 4 volt is, so here the number of bits n is equals to 8 in SAR type ADC, and the conversion time for input voltage of 2 volt is 50 microsecond, and in question it is asking the conversion time required for converting input voltage of 4 volt. So, as we know that conversion time of SAR type of ADC depends only on the number of beats and it does not depend upon the input voltage. So, whatever is the input voltage, for all the voltages this kind of ADC will have same conversion time, that is 50 microseconds. Now, the next question is, a 12-bit ADC is operating with a 1 microsecond clock pulse period and total conversion time is seen to be 14 microsecond. The ADC must be, so here we have number of beats given which is 12 and total conversion time which is given is 14 microsecond. Here we have 4 kind of ADCs: successive approximation, flash type, counter type and integrator type. So, integrator type, dual slope integrator and single slope integrator type ADCs, they require 2 into 2 to the power n minus 1 in worst case, n plus 1 sorry, in worst case. So, 12 and 14 are very close, numbers are very close. In counter type ADC, number of counts required are 2 to the power n minus 1. In flash type, number of counts is only 1, and in successive approximation type, number of count is equal to 12. So, here clock pulse is, time period is 1 microsecond and number of beats is 12. So, multiplying clock pulse and number of beats, we get 12. So, successive approximation type ADC will give most close result, but here in the question we have given that the conversion time is seen equal to 14 microsecond. So, 2 extra microseconds delay may be here due to SOC or EOC signal or some other components. So, the most correct option for this question is successive approximation type ADC. Next question is, among the following slowest kind of ADC. So, just now we have compared and after comparison we found that the slowest kind of ADC is dual slope integrator type of ADC. So, B is correct option. Now, next question is, a dual slope ADC has R is equal to 100 kilo ohm and C is equals to 0.01 microfarad. The reference voltage is 10 volt and fixed integration time is 10 millisecond. The conversion time for 6.8 volt input in millisecond is, so it is a numerical based on dual slope ADC and this numerical is formula based completely. I am just hinting you the formula which you have to use, do the calculation yourself and get the result. So, you have to use the formula T1 plus A Vref into T2. You can find this formula in dual slope ADC design explanation. So, you will get the result as 16.8, means B is going to be the correct option. Try to calculate yourself. The next question is, advantage of using dual slope ADC in digital voltmeter is that, so dual slope ADC has advantage that it is more accurate and it has high resolution, and due to these reasons it is used in all measuring instruments, even in the digital voltmeter. So, from all options D is the correct because it has written its accuracy is high. So, try some more objective questions yourself. With this we come to an end of this lecture. In this lecture we discussed about design of 3 different kind of ADCs. First one was successive approximation type ADC, second one was single slope type ADC and third one was dual slope type ADC. Also, we discussed about advantages and disadvantages of all type of ADCs and compared all type of ADCs. So, with this let us wind up this lecture. Happy learning.